in the first part of this section, we only looked at open fluids which had no contact with external walls. And obviously this is in reality very rare. And you have, especially in microfluidics, a lot of contact with between solids and liquids. And this is what this section of the lecture is about. So we want to understand what happens close to the solid liquid interface. In general, solids have a chemical potential at the solid liquid interface, and this results in a charge, in this case depicted by the positive signs in the figure on the right hand side. And typical or easy examples to understand this is if you work with surface treatments. So it's possible that you have little groups of certain molecules like chloride or ammonia attached on the outer layer of your wall. Obviously, then you directly see where this charge comes from. So the interaction between liquid and solid can be described by various models. And the keyword to find these models is dielectric double layer. In this lecture, we will cover 3 models, and we will start with the easiest one, which is called Helmholtz model. So the idea of the Helmholtz model is that every surface charge is met by a particle of the opposite charge. So positive charged wall means that it attracts negatively charged particles, and they meet each other close to the interface. The rest of the liquid, the so-called bulk solution, is neutrally charged because there are also negatively charged particles within the bulk solution because there are enough of them in the solution anyhow, so that you can't really get all of them close to the wall. And if we now take the Poisson equation, you know that there are no sources or sinks within this electric field. And this means that the right-hand side of your equation has to be 0. And to now get the potential along your x-axis within this picture, we only have to solve the equation. So we have to integrate it twice. And you will see that the first integration results in a constant. And the second integration will give you an additional constant phi0. And it will also add the variable x to your equation. Consequently, if you look at the electric potential, you see that it's linear and it decreases the further away you are from the wall until to the position r, which is the radius of your particle, and then it is 0 along the x-axis. So this very simple model is only valid if you have a very high electrolyte concentration, or if you're working at very low temperatures of about 0 Kelvin. The limitations of the Helmholtz model already show that there is another important parameter that needs to consider to get closer to reality. And if you look at 0 Kelvin, there's usually no thermal motion of your particles left. But if you're at a room temperature or even higher temperatures, the thermal motion becomes important. And this is what is considered in the second model that we discussed today, the Guy-Chapman model. It also considers the diffusion of ions within your liquid. And to describe this model and the electric potential, we need to work with the Boltzmann equation. And specifically the Boltzmann equation in electrostatic fields, which is described down here. So you have the concentration of the ions, which is given by minus the bulk ion concentration, so in the total liquid, times an exponential function of a valence, the valence number set, the electrical elementary charge, phi, and divided by the Boltzmann constant times the temperature. So let's start again from the Poisson equation. What we need to describe now is the electric density, and this can be done with the Boltzmann equation. What we just have to consider is that we know the concentration of all ions at their respective position, which is the right-hand side here. And we need to do it for every ion within our liquid. That's why we have a sum. And we need to multiply the concentration times the charge of this particular ion. So its valence number times its elementary charge. The solving of this equation looks quite complicated. And that's why we simplify the right-hand side of our equation by linearizing it. The linearization can be done by a Taylor-Rowe development or similar approaches, but it's not scope of this lecture. That's why we just skip it. But if you do it, you end up with this middle term. So that we introduce a parameter to describe this part of the middle term, which we call the Debye length. And so this term is equal to 1 divided by the Debye length to the power of 2. And now the differential equation looks quite simple. You only have the second derivative of the electric potential, which equals to the 1 divided by the Debye length to the power 2 times the electric potential. And this can be, so that there is a very simple solution, which is written here. So phi equals to a constant times the exponential function x divided by the Debye length plus a second constant times the exponential function of the negative x divided by the Debye length. Use the boundary conditions of our setup. The first one is logical. So if you move far away from the solid liquid interface here, you will have no electrostatic potential because then you're only in the bulk solution. So if we say that x goes to infinity, the electric potential would equal to 0. And this automatically means C1 equals to 0 because the right-hand side of this term, this complete term, is going to be 0 if x goes to infinity. The second boundary condition that we assume is that we know at the position 0 here at the interface the potential, and we call it phi 0. And that's why we end up with C2 equals to phi 0. This solution then is written here. And keep in mind the Debye length is defined by the equation that we just derived a minute ago. If you look now at this, potential, you see that it's slowly decreasing the further away you move from the wall, and that it's decreasing with an exponential growth function. So the model that we describe here, so the Guy-Chapman model, is not really functional for high electrolyte concentrations, and you have to move back to the Helmholtz model. But in general, it's more realistic. The last model that we talk about is the so-called Stern model. And it is a combination of the other two models that we just learned about. So we assume in the Stern model that there is a rigid ion layer close to the surface, and that there is a diffusion behavior further away from the from this rigid layer of ions. And both of these phenomena can be described based on the two equations that we just derived. So you have a linear change in the electric potential in the first layer from 0, x equals to 0, to the radius of your ion. And further away, you have the exponential behavior of the electric potential. So close to the surface, the potential is linear, and then you get an exponential change of your potential. And there are many more models to describe the dielectric double layer, but I think those three give you a good impression on what happens close to the surface, and they show that you have to consider basically two important effects: the electric attraction of the molecules to the wall, as well as the thermal based diffusion of the ions within your liquids. To finish this video, we will talk about a parameter called zeta potential. And this is depicted on the right-hand side. So in general, we assume that particles or ions will move along with the flow. So let's say there's a flow into the right direction. And generally, particles follow this flow because of viscous forces. So the friction will keep the particles along with the fluid. However, if you are close to the wall, the attraction forces get between the wall and the ions get stronger and stronger. And at one point of time, this attraction is stronger than the attraction by the friction. And usually we assume that this distance, when particles are dragged along with the liquid, is the Debye length that we just derived a few minutes ago. So if you put this into numbers, you can say that the zeta potential is defined by the electric potential of the shear plane. So the zeta potential equals to the electric potential of the shear plane minus the electric potential of the bulk solution. So this is this difference. And it is usually given by the Debye length. So if you enter the Debye length into your potential equation, you will get, in general, the zeta potential.